Let's break this up. We've got Newton's 3 laws of motion for matter. Now it applies to liquids and gases too, but a little tricky there. There's ways in which you deal with that, but we'll just talk about solid objects. I'm going to do the first law for this video, then the second law I'll add on, and the third law. And what I want you to do is get your book out and just read along. There's some subtlety here, something that you won't find anywhere else yet, too. Because this law is called Newton's first law of motion. Now we got to give props to Galileo. This is where Newton leapt off of, right? So realizing this, so you can call it Galileo's first law, really, in the homework. I'm going to say it simply. You've got a little more complete statement in here. Here's the law. If all forces, pushes and pulls of any kind, touching, even not touching, if all the forces on an object, so pick an object, any object you want, whatever object you want, if all forces on an object are balanced, if they balance like a tug of war in any direction, they're all balanced. We call that equilibrium. You're going to need that, especially when we get to stars and we talk about hydrostatic equilibrium. Remember, you heard that before. Then what? Then the object, whichever object you're talking about, cannot and will not accelerate. Absolutely. Not. These are not laws you can break, luckily, so you don't have to worry about getting a ticket for this law. You're not breaking it. What does that mean? What does that look like? Well, let me draw 2 cases. The first one you're used to, right? The first one you're used to. Look at that object. Is it accelerating? If you say the object is not accelerating, then you know whatever the forces are, however they could be 10 forces on it, pushes and pulls, but they must be in balance. And so what does that look like? That looks like this. There's something not moving. If all forces balance, it can't start moving. To start moving would be to accelerate. Right? You need examples of that? Well, just look around the room. Anything, wherever, right? Anything, just anything there, anything. Notice, no, that's accelerating. If it did, it'd be weird. Right? So that means that all the forces are balanced. Now, keeping track of all the forces can be tricky, but that's true. But what if it's moving? Now, we have trouble with this because we think of, well, I got to get it moving. Fine. Maybe while you get it moving, or for whatever reason it got moving. But if it's moving, somehow it got moving, don't worry about that. If something is moving, there's a little arrow for motion or velocity going that way. If it's moving, and then all of a sudden, suddenly, the forces are all balanced. The pushes and pulls, you got same strengths and directions. Then what does it mean to not accelerate? It means you cannot go faster. You cannot go slower. You can't stop. And you cannot turn. Aristotle got this wrong. So it's okay. Let me just go here, here. Can't do what? Increase speed, decrease speed. It can't stop. It can't turn. That's important, especially the turning one for astronomy. Why? Think about orbits. It can't what? It can't accelerate. Why? Because it's the force, in this special case, if all the forces are balanced. Now, if there's no force, that's true too. So often this is stated, if there are no forces. Well, good luck finding that in your room because pull of gravity, right? So, yeah, you can imagine no force. That's all Newton's first law is, but it is a shift. It's counterintuitive. Why is it counterintuitive? I'll show you. When we're done with these, we're going to apply this to astronomy, right? This will all kind of see about your thinking and see which law is doing what. For now, check it out. Remember Aristotle? He said things go home, kick back, watch the game. Now I can make things do stuff, but when I stop, it's just going to go to its natural place and kick back. It's going to stop. Is that always true? What if it's not as rough? See, because I increase the speed, so the forces aren't balanced there. And once I increase the speed, it decreases its speed, so the forces couldn't have been balanced. According to this. According to Aristotle, that's natural, but no, it isn't. Because you smooth it out, it goes farther. You smooth it out more, it'll go farther. You get a hockey puck on a smoothly just finished ice rink. A little sheet of water there. Does it increase speed? Not much. Doesn't really increase speed, right? While you push it. Does it decrease speed? There, not much. Probably maybe a little bit, I don't know. Does it turn? No. Right, so it's going to go, just think of that image. Right? And let me show you why that's weird. A couple of places. So we are used to there being friction, there being things that are going to stop us and stop objects. But take a look at what this tells us. 1, 2, yeah, let's do it that way. All right. Now, the first case where it's just sitting there, that kind of makes sense. If all the forces are balanced, it's not going to move. But what if it's moving? Check this out. Check this out. Let's do the first one. Do the first one first. Okay. There you are. Why do I have this? I'm going to start it moving. Okay. And that's your head right there. You little alien. I'm going to start it moving. I'm going to accelerate. Right now it's not accelerating. What can you tell me? All the forces are balanced on every single thing. Do you know all the forces? Maybe, maybe not. I don't know. There's whatever forces. Now I'm going to accelerate it. I'm going to increase its speed. But the inertia of your head says, I don't like to accelerate. So it wants to, the inertia wants to just, it's sitting there, it wants to sit there. You're going to have to make it accelerate. Watch what happens to your head. Right? I don't know if you saw it, fell right there. Let's do it in slow motion. And let's see why people speak of this incorrectly. What happens? I'm losing my head. No. Okay. Here you are. Your friend steps on the gas. Your head's sitting there. It wants to sit there. You're gonna have to make it speed up. So initially it goes like this. Initially your head's like, and then it gets pulled along. We often say, oh, now I got whiplash. If you're sitting at a stoplight and someone hits you from behind, you go like this. Oh, my head got thrown back. No, it didn't. No, it didn't. Your head's just got a lot of mass. I can't help that. It's just a big old massive inertia head, right? And then maybe hopefully your neck and your neck will pull your head along, and then you'll go like that. But that's because it was at rest. But what if it's moving? What if it's moving? If it's moving, it wants to keep moving. It wants to keep moving. Let's see if I can do this. It's gonna be tricky. So I get it moving. I gotta get it moving first. It's moving along. I know I gotta accelerate to get it moving, forget about that. Once it's moving, it wants to keep moving. No decrease in speed, no increase in speed, no turning. Just keep moving. Watch, your head wants to keep moving. What's it do when you slow the car down? I did it. That was wrong. Because I pulled back and, see, experiments, you gotta repeat them, don't you? Yeah, I did that on purpose, not really. Okay, so, let me go out here. Can you see that? I'm gonna get it moving. Once it's moving, yeah. I'm going to stop it. Well, you know, what's your body do when someone hits the brakes? Doesn't it keep going forward? Try to get this going. You stop it. Anyway, it keeps going forward. Your head goes, ah, right? What? Here. I don't know if you can see me. Just walk into something. You walk like this. Ah, my head kept going. Why? Because it's got inertia. It's like when you got to do your homework and you got inertia. That's the biggest power move right there, is to get started. Literally, that's a psychological analogy. It's not a physical thing. Well, let me show you this one more time and show you this law, Newton's first law, Galileo's first law. If something is moving and all the forces are balanced, it cannot increase speed, it cannot decrease speed, and it cannot turn. And it won't. If it does any of those things, you got to blame someone. Yeah, that's decreasing speed. Let's not worry about it. I'm going to increase the speed. And then it decreases. Why? Because of the roughness. Things don't decrease speed on their own. They will go forever. That's not what, oops, we're not used to seeing that. It's also turning though, isn't it? That's important for astronomy. What's making it turn? Something's got to make it turn. We're getting right into Newton's second law right here, because Newton's second law is just the opposites. Okay. I made it increase speed, and then there's this friction and these little bumps, but it's turning. Can something go around in perfect circles out in the heavens because they're heavenly? No. They have to be made to turn. If something's turning, you have to either pull it in or push it in to make it turn. It has to be pulled in or it has to be pushed in to make something turn. Try it. Tie something on like a ball, something maybe better than a ping pong ball, and you spin it around. And what happens when you let it go? Well, it's kind of tricky. It's kind of a tricky thing. And so when things get tricky, rely on the law, because that's happening, right? So I go like this, I increase the speed. It's turning, so it's accelerating. Something's got to make it accelerate. Oh yeah, I got a string. I can do it this way too. But the minute I let it go, it flies off, right? And then of course there is gravity here, so it would be like that, but if it was floating in space, it would just go, floating in space, it would just go straight. Never, ever, ever, ever decreasing speed or increasing speed or turning. Ever. You're floating in space, that's it. Now, we're going to find out ways, if you're floating in space, to increase speed, decrease speed, or turn. Got it? Things go straight. If they're moving, they will go straight forever. Straight, no turning. At the same speed, forever. If one condition must be met, what? All the pushes and pulls on it are balanced. And if there's no pushes and pulls, great, out in space. But here you've got friction and various things. So you're driving down the freeway. Well, oh, no. I'm not going to give that to you yet. I'm going to do that as a quiz. Okay, now, next video. Newton's second law follows right after this. And I'm just going to give you a break so you can pause.